Hello everyone, welcome to Dev Summit and welcome to this workshop. My name is Hong Xu. I'm a product engineer on Rust team, and my co-presenter Shenlan Zhen is also a product engineer on the same team. In this workshop, we're going to talk about how you can perform image analysis in ArcGIS using Python, and we'll be focusing on time series imagery. We'll begin with an overview of image analysis capability in ArcGIS platform so that you'll get a whole picture on what type of analysis you can do. Then we'll introduce ArcGIS Python programming environment, which includes ArcPy and ArcGIS API for Python, discussing image analysis API and the two typical workflows for time series image analysis, which are raster collection and multidimensional raster. We have full demos covering many aspects of image analysis, from mapping water from Landsat time series, analyzing land cover changes using linear spectral mixing, to detect forest disturbances using land trend algorithm, which is a newly added feature in most recent release, and also modeling urban growth using nighttime light data. Two demos for each workflow, and for the sake of time, for each demo, we'll use either ArcPy or API for Python, but you can use any product for these workflows. ArcGIS is a platform for imagery. You can manage many types of imagery from different sensor platforms, process and auto-rectify imagery, visualize imagery, and perform all kinds of image analysis, which is the focus of our session. For analysis, ArcGIS supports pixel-based image classification, such as random forest, support vector machine. ArcGIS also supports deep learning. You can extract features and perform object-based detection and classification. There are many multidimensional analysis tools for analyzing time series imagery, such as trend analysis and change detection of time series imagery. There are rich spectral index calculation algorithms, NDVA, NDWA, and so on. The list in the slide is only a small portion, and you can do custom indexing calculation using band arithmetic function as well. The spatial analysis capabilities include hillshade, interpolation, slope, distance, hydrology calculation, and so on. These capabilities are all available as functions, geoprocessing tools, or service tools, which you can access using Python. You can also extend analysis capability by leveraging other libraries, NumPy, Esri, SciPy, and so on, to develop custom functions with your own algorithms. Python is a great way to do data science and perform image analysis. And ArcGIS comes with the product that allow you to leverage the image analysis capabilities with the programming language you are familiar with. ArcPy is for desktop applications. You use ArcPy to access your local data or web layers. The processing is done locally, and the result is saved on your local machine. ArcGIS API for Python is for web applications. Here you work with web layers, image layers. The processing is distributed across enterprise servers, and the output is an image layer hosted by server. For image service, there is a special feature which is on-the-fly server-side processing that both products can leverage. So for image analysis, the programming pattern is very similar between the two products, ArcPy and API for Python. To bring everyone on the same page, I'd like to review some concepts that will be used in the presentation. Mosaic dataset is a data model for managing collection of images. It can manage many types of image data, Landsat, Sentinel data, MODIS, and so on. It is scalable because it uses a geodata table to manage and catalog the metadata of the images, not the pixels. It references the data and the Mosaic pixels on the fly. Mosaic dataset is also flexible. You can add images, delete images from the Mosaic dataset, and update the data easily. Multidimensional raster is a special raster dataset. It stores well-structured multidimensional info such as variables, time, depth, and an example of the data is time series satellite data with time, or ocean temperature data with time and depth. A multidimensional raster can be saved as a CRF, cloud raster format, or a Mosaic dataset with multidimensional info, or other formats such as Landsat. RAS function is an algorithm definition for processing RAS data. It has the capability to process the data on the fly. ArcGIS comes with many RAS functions out of the box, and you can chain these functions to solve complex problems. You can also save the functions as a raster function template, RFT, to share with your coworker or users. Image server is an ArcGIS server that processes and shares RAS data through the web. Image server serves image services and supports on-the-fly processing as well as distributed raster analytics through Portal for ArcGIS. To analyze time series imagery with Python, ArcGIS has two classes and supports two typical workflows. One is through raster collection, and one is through multidimensional raster. In this diagram, you can see the first workflow is you create a raster collection from a folder of image or a Mosaic dataset or image service, and use raster functions to work with the collection. The other workflow is that you create a multidimensional raster directly from the dataset or convert from a collection. With multidimensional raster, you can use many multidimensional analysis tools to analyze your time series imagery. We will be discussing and demonstrating the two workflows in detail. Before jumping into the two workflows, I'd like to use a simple case to warm you up. It is a ArcPy code snippet. It creates an NDVI raster from a single Landsat scene and display with a color map. So first it imports ArcPy module and create a raster object from the product file using arcpy.raster. Then use mask function to mask out the black pixels by setting no data value to be 0. And then use NDVI function to compute an NDVI raster and display with a color map. So a few lines of code, you get your result. And all the process done on the fly. We didn't save any step. Now we're ready for a workflow discussion, and I'm passing to my colleague Shen, who will talk about raster collection workflow.
Thanks, Hong. I'm going to talk about how to process a series of images using the raster collection object. We often have a stack of images across a long period of time that we need to process in order to analyze the changes that have happened. Raster collection is a powerful way to handle this task. This diagram shows the basic workflow. First, we need to create a raster collection object. It can be created from a list of images, a Mosaic dataset, an image service, and a multidimensional raster. Then, we can filter the raster collection using various criteria such as location, time, and other raster properties to get the images that we need. Then we can map some function to the raster collection, and the function will be applied to each raster within the raster collection. The function can be as simple as calculating NDVI or a complex algorithm, which we will see in the following demos. And finally, we can reduce the raster collection to get meaningful information from the data. Now, I will go through two demos to illustrate how this works in the real scientific applications. The first demo I'm going to show is mapping glacial lakes in Alaska using the Landsat time series. Glaciers worldwide are rapidly retreating due to climate change. As they retreat, lakes will often form in their terminus, like in this region here. These lakes pose serious risks of flooding to people in the downstream region. This demo is inspired by a paper published recently in Nature Climate Change that examines changes in glacial lakes over the past decades. This is written using the ArcGIS API for Python, which can be run in a scalable server environment. The workflow is as follows. First, we filter the Landsat collection to get a raster collection for the first 5 years. Then we calculate a series of indices such as NDWI and NDSI on each of the image within the raster collection using the map function. We take thresholds of these indices and combine them together to identify water. Then we take the mean of the raster collection of the binary water images to obtain a water occurrence frequency image. Finally, we conduct post-processing to filter out water bodies that are not glacial lakes. This process is iterated until the entire Landsat collection has been processed. Now let's look at the workflow in more details. In the first step, we import necessary ArcGIS API for Python modules. We establish a connection to the server portal, and we define relevant parameters for data processing. In the second step, we go through the Landsat files in the data store hosted on our server to gather relevant information that is needed to create the raster collection. The information we're getting here from the files include file names, the acquisition type, and the sensor type. Then we create the raster collection by feeding the information that we just gathered. I also loaded a digital elevation model here to calculate the slope, as well as a Glacier polygon shapefile that we will use later. Here I printed out the attributes of the raster collection. You can see the information we gathered from the previous step. And here is an image example from the collection. In the third step, I first defined the map algorithm used to detect water from the raster collection. The algorithm is mainly based on thresholding band indices and band values. A pixel is considered water if its NDWI and NDSI values meet certain thresholds that we have defined earlier. Now we are ready to conduct the actual mapping. In this for loop, I filtered the Landsat collection for every 5-year periods and applied the map function for water detection. The mean function here gives us the frequency that a pixel is considered as water in the map function. Then we further apply thresholds of band indices, band values, slope values, and elevation values to filter out misclassifications such as cloud shadows, as well as other water bodies that are unlikely to be glacial lakes. Then we convert the water raster to water polygons and remove background polygons that are not water bodies. We expand the water polygons and then dissolve the overlapping ones to merge adjacent water polygons that may have been separated due to data quality issues. The dissolved polygons are then shrunk to preserve their original area. Next, we conduct a final set of filters based on the average slope within the polygon area, as well as the polygon distance to glaciers. Here we create a table that contains the average slope within each polygon and join the table to the polygon so that we can remove polygons that that have too large of a slope or that are too small in area. And finally, we remove polygons that are more than 1 kilometer away from glaciers. These steps further remove non-glacial lakes polygons from our results. Here are some visualizations of the result. We can see that we've outputted 4 glacial lake polygon layers from 2000 to 2015 in 5-year intervals. These layers are stored on the server. I put the 2000 and 2015 result on top of each other here. This darker blue polygon shows the extent of this lake in 2000, and this lighter blue area shows where the lake has expanded to in 2015. And we can clearly see the drastic retreat of these glaciers over the 15-year period. In the second demo, I will show you how we can use linear spectral mixing to analyze land cover changes around Lake Tahoe. This time we're going to switch to ArcGIS, which can be run directly in ArcGIS Pro. The methods and function names will look different, but the functionalities are equivalent. A pixel collected from an image can contain a single pure land cover type. For example, this pixel here only contains non-photosynthetic vegetation. This one here contains bare soil, and this one here only contains photosynthetic vegetation. But more often than not, a pixel contains mixed information of different land cover types. For example, this pixel here contains all 3 types. So the goal of spectral mixing is to identify the fraction of each type in order to study the composition of the land cover. The 3 land cover types we're going to mix here are non-photosynthetic vegetation, photosynthetic vegetation, and bare soil. These are called end members. After we identify the end members, the algorithm can tell us in each mixed pixel in the image, such as this one, how much of it is composed of non-photosynthetic vegetation, how much of it is photosynthetic vegetation, and how much is bare soil. The workflow is similar to the first demo in that we're still doing map and reduce on the raster collection, but we don't have any complicated thresholding and filtering algorithm here. We first create a raster collection out of this Mosaic dataset. It contains 1,087 rasters. Then we filter the raster collection using an area of interest as well as time to reduce it down to 126 rasters. This table shows the attributes of the raster collection. All of them are obtained directly from the Mosaic dataset. And this is a visualization of a cloud-free image, and this is Lake Tahoe. In the third step, we define a map function to clean the image and remove bad pixels that are water, snow or ice, cloud, and cloud shadow. This can be done using the QA flags in the QA band of the dataset. We need to do this because we're not interested in these features, and including them will interfere with the mixing algorithm because we don't have end members for them. In step 4, we conduct the linear mixing. I've collected polygons of these end members from the image, so I will use them directly here. You can also create your own training data using the image classification wizard in ArcGIS Pro. Then I can simply call the linear mixing API, feed the image, the training data containing the end members, as well as other optional parameters to conduct the classification. And here are the results. This is the same image as shown before, but classified to bare soil in red, photosynthetic vegetation in green, and non-photosynthetic vegetation in blue. Finally, we reduced this resulting raster collection to perform some quantitative analysis. We clip the raster collection to an area of interest and get the time series of the average fraction of the three members, and we plot it over time. We can see that in our study area, photosynthetic vegetation used to be dominant. On average, it covered about 90% of the region. Around 1992, there was a drastic decrease of photosynthetic vegetation and an increase of bare soil, and the fraction remained relatively stable afterwards. After digging around on the internet, we find that there was a Cleveland fire that happened in 1992 in El Dorado National Forest, which is west of Lake Tahoe. This fire explains the drastic pattern as revealed by our analysis. Back to you, Hong.
Thank you, Sean. So you've learned analyzing time series imagery using raster collection workflow. Now let's look at the other workflow, processing using multidimensional raster. If you have a multidimensional raster dataset, you can create a raster object directly from the dataset. You can also create from raster collection using the two multidimensional raster method. Once you have a multidimensional raster, you can analyze using multidimensional raster analysis tools. ArcGIS supports many multidimensional raster analysis capabilities. For time series change detection, ArcGIS supports two algorithms. One is CCDC, Continuous Change Detection and Classification. It worked with dense time series data. For example, use all available Landsat scenes over the study area. For each pixel time series, it performs a harmonic regression, detecting the time at which model breaks, and that time is the change time. So you can get earliest change, latest change, largest change from the time series. The pixel values in the input time series data are different at different seasons. However, in the output regression model, which we call it change analysis raster, the pixel values are same across time within one harmonic curve. The harmonic function takes account of the seasonality. So change analysis raster can be used as an input for classifying the time series. The other is Landsat, Landsat-based detection of trends and disturbances. This algorithm works with yearly data. It performs temporal segmentation to identify vertices and form segments. The segment has start time, end time, duration, and magnitude. So you can extract many useful information, like change start time, ending time, change magnitude, and change durations. The multidimensional analysis capabilities also include trend analysis. We support linear trend model, harmonic trend model, which can create annual and seasonal trend and generate trend raster. For example, you can calculate vegetation trend from satellite imagery. With output trend raster that store the trend model, we can predict and generate new time series data for future time. There are also tools to aggregate your data based on temporal resolution, calculate anomaly, and perform other multidimensional raster analysis. We have two demos for this workflow. In the first demo, we'll analyze timber harvest pattern using land trender algorithm. The study area is in Western Cascades Forest, a large commercial timber production area in Oregon State. We want to understand the spatial and temporal patterns of timber harvest. The diagram shows the processing workflow. The input time series data is Landsat imagery of summer season from 1984 to 2020. And I had created a multidimensional raster from this time series. This will be our input. And first, we'll create a normalized burn ratio raster from it because it is effective in detecting forest disturbances. Then we'll analyze using Landsat tool to generate a change analysis raster. And from there, we'll create logging disturbance map, create recovery map, and also classify the whole time series imagery. In this demo, I'm using ArcGIS and Jupyter Notebooks. Here I import ArcGIS and also ArcGIS.RA module, which is the image analysis module. It has all the image analysis APIs that we will be using in this demo. Also check out image analyst license and define environment setting for parallel processing because change detection tools support parallel processing. The first step is to create a raster from the input using ArcGIS.raster. Because the input is a multidimensional raster, so I set the second parameters to be true and use variable property. We can see it has total 80 slices, and this is the display. And by default, it displays the first slice. Second step, I create an NBR raster, normalized burn ratio index raster, using this NBR function, specifying the shortwave band ID and the infrared band ID, and then use render function to display with a color map. This NBR raster will be the input to our land trend analysis. So the third step is performing land trend analysis. I use analyze change using land trender tool and generate a change analysis raster. Here, the input raster is the NBR raster we just calculated. And I also define a snapping date, which allows the algorithm to choose a good clear pixel if there are multiple images within a year. Having multiple images for a year can reduce the possibilities of getting no data in the output because of cloud and shadows. And also define a maximum number of segments to be 5. This will reduce the noise and avoid subtle changes. Take the rest as default and save the result. As you can see that the output is a multiband, a multidimensional multiband raster. I render 3 bands, first, third, and fifth band with RGB. The 3 bands are slope, fitted value, and magnitude. Pixels with purple colors have larger slope, meaning big change or disturbances. Green color is forest. And next, we'll derive information from the change analysis raster. First, we'll detect the abrupt decrease. I use detect change using change analysis raster tool, where I set change direction as decrease, as logging is a type of abrupt decrease. Set duration is within 4 years, and the magnitude is about 2.4. This value is the estimate of the NBR value change from forest to disturbance. Then I go ahead to process and generate disturbance raster. To display the result, I apply a render function with a color map. This is a screenshot of the result overlay on top of a base map layer, so the patterns can stand out. The pixel values are dates. Pixels with light yellow means change started in early years. Dark brown means change happened in recent years. The harvest seems to started from the center of the region and then expands out along the rows. The regular square cut pattern is due to forest protection. Left is a state park. There is no logging. And on right is a protected forest. Some logging happened in early years when protection has not been regulated yet. So many information can be interpreted from this disturbance map. Next, we'll look at recovery process. How long for these disturbance pixels to recover and become trees? So here's the workflow. We retrieve increasing segments, then get the start dates and ending date of the segments, then do a minus operation to get the duration. It is the number of days. Then we convert the number of days to years by dividing by 365. So the code simply calls detect change using change analysis raster tool to get the from year and ending year of the increasing change, then calculate the change duration in years. And again, this is a screenshot of the output duration map overlay on top of base map layer. The pixels are number of years for disturbance pixels to recover to trees. Red means more years, and yellow means less years. The next step is to classify time series imagery to understand the forest change. So we have said that earlier we can use change analysis raster to classify the time series imagery. I created a raster from the change analysis raster that we generated earlier. And the input samples are collected using PRO's training sample manager. Here we define 4 classes: forest, disturbance, recovery, and slow recovery. I use train random tree classifier tool to train, where the input raster is the change analysis raster. I also set a dimensional field here, which is the time field created when I collect the training sample. These training samples are labeled the years in which samples were collected. Then train and get a class definition file, which is the .ecd file. And use classify raster tool to classify the time series data using the trained class definition. Display the classified time series. Green is forest, dark red is disturbance, yellow are recoveries. And finally, I used Summarize Categorical Raster tool, which is a new tool in Pro 2.7 to create a class summary table. It computes pixel counts for each class at each time and create a chart from the table to visualize 3 classes. So now we can see forest changes through time. That was how you can leverage the multidimensional analysis capability to perform time series analysis. The second demo is modeling and predicting urban growth using nighttime light imagery. Research has suggested that nighttime light can be used as a proxy to population, economic growth, and urbanization. So I'm going to apply ArcGIS trend analysis capability to the nighttime light data to look at the urbanization pattern in a global scale. In this demo, I'll use ArcGIS API for Python and Jupyter Notebooks. The input is an image service with nighttime light data from 1992 to 2013 across 22 years. We'll create a raster collection from the service first, then create a multidimensional raster from the raster collection so that we can use trend tool to perform trend analysis. The trend analysis generates a trend raster which stores the trend model. It is a multiband raster with a slope band, an offset, and RMSE. Then we use this trend raster as an input to predict and create a service with predicted future nighttime data. To start, we include ArcGIS module, raster module, and create a GIS object from the portal. Then we create a raster collection from the service URL, which is the image service that on the portal. So this is the catalog table, and with many fields. You can see product field and the time, and also variables, which will be used later. The second step is to create a multidimensional raster from the collection. Here I use two multidimensional raster methods and specify the variable name to be variable and dimension name to be SDD time. We can use variables property to see the multidimensional raster has a dimension SDD time and 22 slices. And we can get the dimension values using getDimensionValue method. To get the first slice, we use multidimensional filter function by specifying a dimensional value and then render it with a stretch function to display the image. The third step is to perform trend analysis. Since the service is yearly based, I use Generate Trend service tool with linear regression type. The output trend raster is a multiband, where the first band is slope, and it can be used to represent trend. Positive means increasing, negative means decreasing. Instead of use a simple stretch render, I want to use red to RGB function, which maps the positive slope to a red band and negative slope to blue band, and the green band is the offset. So then apply a stretch function, and then we can get this beautiful trend map. In this map, red color means increasing night lights, and blue means decreasing night lights. Green means no change. You can see the dominant red color across Asian countries like India and China indicate a trend of a growing trend of population growth and urbanization. In the West, in the United States, the trend varies spatially. The green spots surrounded by red indicate central cities have been developed and are expanding outwards. The last step is to predict. Here I use predict using trend service tool with the trend raster we just generated as the input, and set a starting time, which is 2020, and then an ending time, which is 2030, 10 years, and then 1 year as an interval. Then we obtain a nighttime light time series from 2020 to 2030. So the output is a hosted image service. And as seen before, we use multidimensional filter function to filter one slice and display. To compare, I create two maps side by side. Left is the beginning nighttime light, which is 1992, and the right is the predicted nighttime light in 2030. So you can see a dramatic difference. So that was how you can create a multidimensional raster from a raster collection and perform trend analysis. We went through the Python workflow for processing time series imagery and demoed 4 use cases. Hope these are useful for your work. In the demo, I used the multidimensional raster input. You might wonder how to create a multidimensional raster out of the Landsat time series imagery. You can use 3 GP tools with 3 steps. First, create an initial Mosaic dataset as the container using create a Mosaic dataset GP2. Then using add rasters to Mosaic dataset GP2 to add a folder of your Landsat imagery to the Mosaic dataset. Then build multidimensional info. I have a link to a blog that shows the detailed steps. Another thing I like to mention is the data quality. For time series imagery analysis, the radiometric consistency across the whole time series is important. So I recommend Landsat ARD, analysis ready data, or Landsat collection level 2 data, where you can use surface reflectance product. And also it comes with a QA band, which you can use to mask out the cloud and shadows. For that, I also have a link to a blog which shows the detailed steps. To give you more information, I'd like to point you to some additional useful resources. You can attend some other sessions in this Dev Summit. Working with multidimensional data in ArcGIS session allows you to learn more multidimensional raster management and analysis capabilities. If you are interested in custom raster function or custom raster analysis capabilities, there is also a session for that. There are two demo theaters. One is on change detection, and the other is prediction and trend analysis of raster data. There you can see more demos. And please provide your feedback for this session by clicking on the session survey link directly below the video. And with that, I'd like to end this presentation and get ready for your questions.
Thank you everyone for attending this live session. My name is Lin Tang. I'm the moderator of this live Q&A session. With me are the presenters Hong Xu and San'an Zhang. Also joining us today are one of the developers, Qiandong Guo, who developed the CCDC LandTrender and the linear spectral mixing, those tools that we talk about today in this session. Before we go to the questions, I would like to point out two links. The first link is just below your video. That one is the link to the session survey. We recommended that you please take the survey before you leave. The second link is at the bottom page of the current video webpage. Is the supplemental files. That one points to the presentation slides. So now we are ready for your questions. The first one, Qiandong, can you answer this one? Does the linear spectral mixing tool support hyperspectral imagery?
This is a good question. The answer is yes. It supports hyperspectral imagery. The only requirement is the number of bands for the spectral profile must be equal to that of the image. Thank you.
Hong, can you please answer the next one? Does computing on image server using ArcGIS API for Python use credits?
Okay, so that depends on where the image server is running. So if your image server is an enterprise framework, then it doesn't consume credit, right? But if you use image service and ArcGIS Online, the new technology, yeah, it does. When you run raster analysis tools, it will consume credits.
Good. The next one, San'an, could you please answer this one? Have you had any success using modest HDF rasters with the multiband rasters option in add data and then generating a time series mosaic? This is from BVP.
Yeah, sure. I already partially answered that in the chat. When you want to add HDF rasters or SDF rasters, those scientific formats, you need to use the add multidimensional raster layer option under add data. instead of just using add data, because in that way, you can ArcGIS is able to read the multidimensional data info from those data, and you will read all of the bands as well as their time slices into a raster layer, which depending on the number of slices you have, it is already a time series.
Okay, great.
So Lynn, maybe I can add some additional information.
Sure, go ahead.
Because I just read carefully. Because this means multi-spectral imagery. Because HDF RAS type. So because working with HDF, you use HDF RAS type, and by default, HDF RAS type doesn't support multidimensional multi-band data, right? So because HDF store, the band in separate files. So what you can do is to compose a composite band using a RAS function, compose RAS band, and then use that when you add the data. So if you want to know more information, you can come to me at the Ask Expert channel. Then I can explain more on how to construct the composite band function when you add data.
Okay, great. The next question is also for Hong. This is from Annie. What is Mosaic dataset? Does Mosaic means a lot of small range of remote images, which can be stitched to a panorama?
Yeah, so that is yes, that is one type of application. But in general, Mosaic dataset is a data model that allows you to work with multiple images, bring multiple images together on the fly, Mosaic on the fly. And either the data could be spatially adjacent, overlap, or like, the time series data overlap on top of each other. So Mosaic dataset represent that kind of data model. And then for your case, yeah, it is possible you can Mosaic images together.
Okay, great. Next question. Qiandong, could you please answer this one? Can I use CCDC or Landsat to other type of data that are not Landsat?
This is a great question. The answer is yes. These tools can take other time series data, such as Sentinel, as long as the data meet the requirements, such as the minimum number of observations, minimum number of years. We can run CCDC or Landsat on that data. Thank you.
Great, thank you. The next question is for Hong. If I just want to compare two land cover datasets and see what classes are changed, is there an easy tool to do that? This is a question regarding change detection. Hong, could you please answer this one?
Thank you. Yeah, that's a good question. Yeah, because in this workshop, we focus on time series imagery. But yes, there is a very typical workflow which I know the tool times, and you just want to compare what's the difference, right? Yes, we do support this kind of workflow. And if you like programming, and we have functions and geoprocessing tools like compute raster, and then we can compute the difference between any continuous raster or two categorical raster, and then you can get the combination of all the changes, and as well as the number of pixels that changes in that category, right? So that if you don't like programming, we also have a change detection wizard, so it guides you through all the process. Yeah. So hopefully that's answer your question.
Yeah, it's really exciting to have that change detection wizard, which is very fantastic. I recommend you to try that one. Okay, the next one, Xian, could you please answer this one? Can I edit the lake polygons after I publish to the server?
Yeah, of course. When you save, so in the workflow, when you save the results to the server, it's gonna be a feature layer, and you can either load it to ArcGIS Pro or open up the map viewer, and you can edit the polygons in both platforms.
Okay. And the next one, Sam, could you also answer this one? It's from Manira. Are there other libraries for image processing other than the raster module? And can third-party libraries be imported and used?
Yeah, sure. Definitely. You can convert the rasters into a NumPy array using the arcpy.raster to NumPy array method, and then it will just become a NumPy array that you can process using other libraries that suit you.
All right. The next one is the land trender capability supported in enterprise using RAS analytics? Hong?
Yes. So because the land trender is a new algorithm and it released in Pro 2.7, and on the server side, you can use RAS function to perform land trender change detection analysis, and also use Python API to do that. But then for the user experience, the land trender change detection tools in web, this will be coming in later.
Okay. The next one, in the time series change detection demo, did you have to remove cloud shadows? Hong?
Oh yeah, that's a good question. Yeah, so in the demo, the input is a multidimensional raster, which is created like an image cube that has a cloud and shadow has been removed. And it is actually very important if you perform time series analysis. The data quality is important. So that we use the Landsat surface reflectance product, and this comes with the QA band, the QA band. So we use that QA band to remove the cloud. I actually shared the link in the question. So we have a blog on how to create, remove cloud if you have a QA mask. So you can look at that later.
Okay, all right. I saw a couple of questions asking for the demo notebooks and the scraping. And you can leave your email address in the chat window, and the presenters will be able to send you through your email. And now we go to the next one. It's from Azin. Hi, what data input do I need to be able to extract the impervious surface from a multispectral imagery? Please briefly explain the workflow in both traditional and deep learning methods. Thank you so much. Hong?
That's a a great question, but it's really hard to answer. I'll try my best. So if traditional way is there, multiple ways, right? So if you want to extract the imperious surface, a band index can do a quick job, like you use normalized build up in NDBI should be like normalized build up index, right? And another traditional way could be just use traditional image classification. Like we have random forest, we have support vector machine and so on. What you need to do is just prepare your sample data, train your samples and train. We have these train classifier. and then use the traditional way to classify the imperious surface. And then, of course, this is the new way, deep learning way, which is we have many sessions actually cover this part. There are many examples on like extract roads, extract buildings, and so on. So the typical, the workflow is very similar. You define your training sample and you train using deep learning model. And then we have tools such as classifying using deep learning model so that you can classify your defined classes, pixels, and things like that. So actually, I recommend it to check out many deep learning sessions on this topic. And if you have specific questions on this, particularly, to learn more about deep learning method, you can also go to the Imagery Channel, and then we have deep learning expert over there to answer more questions.
All right. The next question is from Ken. In a recent forest paper, there was almost no correlation between LandChander and CCDC output. Has the accuracy of these methods gotten any better? Qiandong, can you answer this one?
Yeah, this is a great question. We haven't done any accuracy jobs so far because the CCDC and the LandChander is very new algorithm. We just released this last year, but in this year we will definitely do more jobs to verify the accuracy. But from our demo, I think the results are very reasonable to detect the forest degradation and deforestation. Thank you.
All right. Next one is also for Qiandong. What are the minimum number of images per year and the minimum number of years for using CCDC?
This from the CCDC's paper, the minimum number of the observation is 12 per year, and the minimum number of year is 1 year. Thank you.
All right. Let me see. There's one more question. What is the maximum of raster which can be added in a raster collection? Rasters on top of one another. Hong, can you address this one?
What's the number of raster can be? So you mean? So okay. So we have two data models. One is raster collection, or or Mosaic dataset. So there is actually no physical limitation on that because we don't actually store another copy of it. So if you talk about multidimensional raster, which for example, the Mosaic, the multidimensional CRF, and then currently there is a limitation, which is the 16-bit unsigned number of the number of signed integer, so that the most that's the maximum number of images that you can save. But this is purely a limitation that this we in the development that can be improved or just improve later.
Okay. Thank you so much. We are unfortunately running out of time in our live Q&A to join us in this session. Please make sure to fill out the session survey before you leave. If you have additional questions or feedbacks, please join us at our Ask Our Expert showcase channel. If you search for Imagery, Hong and Sen will be able to assist you over there. And also you can find many other subject matter experts over there to answer your questions. Enjoy the rest of your day at Dev Summit 2021. We hope you have a very good day and see you soon next time. And thank you all the presenters and Qiandong as well. Thank you.